Hi, and welcome to this week's episode of the Structural Engineering Podcast with Max and Zach. This week I talk with Elena Danzig about mass timber and one of her current projects utilizing a clever seismic force resisting system. As you'll come to learn, the system is quite often used in structural steel projects, but rare in mass timber. Elena is a timber specialist with Aspect Structural Engineers based in Vancouver, Canada. She brings a large knowledge of complex structures with a passion in timber. Now let's get into this week's episode.
I'm a structural engineer based in Vancouver, BC. I've been here practicing in the field since 2008, and for the last decade, my career has really been in the mass timber world, doing a lot of this stuff. Although I've had some really great kind of wide-ranging experience, the passion projects have always been the mass timber projects.
What has attracted you to mass timber, and in general, why use mass timber in commercial construction?
So there's a lot of reasons to use mass timber, and there's a lot of reasons why I like to use it. We're seeing more of it from a climate perspective. There's a huge argument as it captures carbon rather than cement or steel, which are huge carbon emitters. So there's a really significant sustainability argument for timber. It's also a really beautiful material to work with. So there's a lot of interest in having a higher value of structures that are timber, like a higher value when they're being rented or sold. But then I love it for all of these reasons, but also it's just a really fun, amazing material to design with. Like it really combines.
So now you've heard the term mass timber being used a few times. I wanted to jump in here and discuss what mass timber is. Mass timber is comprised of wood laminations typically made to be large, solid wood panels, columns, or beams, often manufactured off-site. They provide use as load-bearing walls, floors, and roof construction. Mass timber products are thick, compressed layers of wood, creating strong structural load-bearing elements that can be constructed. They're typically formed through laminations, fasteners, or adhesives. Mass timber can complement light frame and hybrid options, and is an environmentally friendly substitute for carbon-intensive materials and building systems. Mass timber is engineered for high-strength ratings like concrete and steel, but are often significantly lighter in weight.
It's an organic, natural material that grows in the ground, and you can't fake it. You can't mimic it. There's nothing else like it. And then you have the science behind timber engineering is really developing and has been over the last couple of decades. So it's like this combo of natural and cutting edge engineering, which is really fun to work with.
Yeah, I couldn't agree more. I've been able to do a couple now. And, the one thing I really like is typically architecture is trying to hide the structure. A lot of architects think a very nice looking building is one that you don't see any of the structure, the backbone of the building. And when you have mass timber, it's, we get the opportunity to almost kind of play architect a little bit, it seems like.
Yeah, absolutely. Suddenly the structure is the architecture and you get to express it, and you have to think about ratios that look nice and connections that look good, and how to increase the value of the building, not just from a structural efficiency perspective, but like what happens when you show this connection, or what happens when you show this piece of wood. And it really gives you an appreciation as a structural engineer, I think, for the important principles of design. Like the timber engineers, and most of the timber engineers that I know, are really careful designers because they're used to their structure being expressed.
What are the challenges when designing a mass timber building that you've come across?
Honestly, the big one tends to be code, because particularly in the US and to some degree in Canada, the codes here just aren't where they are in Europe, and they don't reflect where timber is today as a structural material. So, and that follows some of the research. We need a lot more research locally on developing codes for these systems, given the materials and the connectors that we have. We have a structural material that can do so much if you know how to work with it. And we have a lot of research that's happened worldwide, and we have codes, particularly out of Europe, that really allow you to celebrate it. And working on these projects, particularly in the US, but in Canada too, the codes sometimes tie one hand behind your back and sort of limit what you can actually do. But then the other reality of using timber is you have to appreciate like what its strengths and weaknesses are, and what happens to a piece of wood when you put perpendicular bearing to it, and how does that change the structure? And like, you don't have to think about that with concrete or steel, but the structural mechanics of wood are just so particular and so specific. The way wood behaves over its life, the shrinkage and what happens with moisture, and even how the appearance changes over its life. Like, all of these things tie into structural design of wood.
Early in my career, while designing timber structures in the Northwest, I suggested including steel supports for some large spans. And this was really the first time I was told by a mentor to really put some thought into how the two materials act. Since wood is really a living material that changes with its environment, steel is fairly rigid, not changing too much other than with temperature.
Yeah, exactly. And that makes it maybe more complex, but like, all of that can be managed. You just have to understand it.
So tell us a little bit about the mass timber project that we're going to discuss today that you're a part of.
Okay, so the project's name is Terminus. The owner is DBS, Design Build Services, who's a developer out of in the Victoria area on Vancouver Island in BC. The neat thing about this building is that it's the head office of the developer. So they're the owner and going to be the occupants of the building. So they came into the project knowing it was going to be, they wanted it to be mass timber. They wanted to express the wood. They wanted it to be a couple steps up from a standard office building, and they were willing to pay a little bit more for it. Although, they're still a developer and they don't want to break the bank. So money was still a consideration throughout the project. But from the start, they were really interested in doing what was right for the project and making some riskier choices that ended up panning out really well for the beauty of the final product and the efficiency of the structural system.
Now, was this their first mass timber project?
They've done a lot of hybrid light frame mass timber, so light frame shear walls with mass timber floors. They've done a whole bunch of that. So they were quite used to CLT and glulam as building materials. This was their first all mass timber structure, and it was their first mass timber lateral system, or in this case, it was a hybrid, but it was their first time moving away from kind of the light frame standard that we see a ton of around here. It was also my first project when I joined Aspect. I think it was on like day 2 of my time at Aspect that they handed me this project, and I got to just dive right in at the schematic stage and present some or bring in some pretty cool ideas and systems to the project.
That's really cool. Now, with a mass timber building, do you find yourself interacting more with the owner of the structure, or less, or more or less with the architect than other structures?
Yeah, usually that's the case. There's a lot of architectural, structural coordination. In most mass timber projects, it's best to bring mechanical on board early for that, so you could really solve the whole system, because you've got so much wood exposed. You don't have drop ceilings everywhere. This project was pretty unique in that DBS was both the owner and in many ways the designer. So there was an architect, Jack James Architecture, and he was involved throughout the process, but DBS themselves are designers. So they did a lot of what traditionally would have been under purely the architect scope. So they were really deeply involved with coordination of anything of how this was going to look or what the space was going to be. They were definitely more involved than most owners that I've encountered, at least more involved with the structural components.
So as a structural engineer, how is the design process maybe different with mass timber from a traditional, steel structure?
The differences are probably early on, just understanding what the, say, layout limitations are. So column spacing and how the column spacing might tie into where the panels are coming from. So we knew early on in the project that the panels were going to be structure lam, and that drove how to create efficient column spacing based on what structure lam could produce. That's a really important thing to get right early on. And if you don't have a supplier on board early on, then knowing what the different suppliers can produce makes a big difference and really helps drive an efficient structure. Because if you've got grids that are just make no sense for CLT production, then you've already got an expensive structure. And then the other thing is anytime there's a mass timber project, the lateral system is kind of a big open question. There's not usually an obvious immediate answer. Like if you're doing a concrete building, you're going to have concrete shear walls. If you're doing a steel building, you're probably going to have steel braces, and it's just a matter of laying it out. But with this building, and because the lateral system itself would be expressed to some degree, suddenly it's like everything was fair game. You know, we could have looked at concrete cores, we could have looked at pure steel systems. We ended up looking at a lot of really interesting options in order to keep the lateral system both efficient and ductile, and also really pretty and able to be expressed, and working really well within the timber system. So usually the first thing I think about when I'm sitting down on these mass timber projects is first column spacing, and second, what's the lateral system?
I spoke once with a structural land representative, and they were kind of talking through maybe kind of two different approaches with mass timber. One where the engineer of record, is on board early on. They take more of the role of, foundations and lateral system and kind of preliminary framing, and then structural land hires, a specialty structural engineer to do the final design of mass timber. But then they also said there was an option where the EOR designed everything, and they acted more of as a manufacturer. With your experience on multiple projects, and specifically this one, what have you kind of seen, or what have you been part of?
Yeah, I've definitely been part of all of that, and both sides of it. As an engineer very experienced in timber, my preference is always to own the detailing and own the connection development. However, I also know that each supplier has their own kind of systems and preferences that they like to use based on what their shop can handle, and their supply lines and all of that. So taking it on and designing it all in-house before the project gets issued or tendered, while it's kind of efficient from a structural scope perspective, if you're not really connected to the suppliers, you can miss an important possibility or preference if there's not a supplier already selected. On a project like this, it's kind of the sweet spot, I find, when you go into it, you know who the supplier is going to be, and you can start coordinating with them early on just direction of, do they prefer prefabricated connections or pre-engineered connections, or do they like custom knife plates, and what do they find is more cost effective? And then we can use that to guide our detailing. So keeping it at house, but making sure that we're aligned with whatever the supplier can offer affordably.
So you said column layout and lateral system are kind of the two big ones early on in the project. Talk to us a little bit about the lateral layout. What systems did you look at? What was the philosophy early on?
So we started kind of looking at the height of the building and the code in Canada, and what we could do and what we needed to do based on the seismic region that we were in. And this building's in Langford, which is on Vancouver Island, and it's one of the highest seismic zones in Canada. So we knew going into it, we had to get a lot of ductility into this system. Within the Canadian code, there's timber braces are an option, but not an option that allows for much ductility, and not an option that's particularly well detailed or detailed at all within the code. So the code sort of says if you can show that you have some moderate amount of ductility, then you can use these R factors. So that was like our baseline. If nothing else works, we'll try for that. But if we do that, that's going to drive up the foundation loads and the diaphragm loads and really everything else. So that was our backup plan, or one of our backup plans. But then we took this building as an opportunity to really test out some newer or different technologies that seemed like they could fit within a timber system. One of those was QuakeTech, so that was a friction damper that we went quite deep into looking at. And I really liked that system and liked the idea of that system. But in the end, we ended up rejecting it because that QuakeTech system doesn't have any inherent self-centering capabilities. And some of the research has shown that it sort of walks away, like with the cyclic loading, the drift gets more and more rather than any kind of self-centering that you see in even any basic structure. So we ended up moving away from there and then looking deeply at a combination of BRBs and Tectonus friction dampers, slip friction devices. Between the two of those, we were getting similar performance, and it was kind of a toss-up that ended up being a cost issue, and that's where we went into BRBs.
What type of limitations are you typically seeing with like using a mass timber diaphragm or a CLT diaphragm? Are most of these structures, especially in high seismic, utilizing the CLT as the diaphragm, or are you topping it with concrete or plywood, or what has your experience been?
When we can use the CLT, well, to start with, if there's concrete topping needed for either composite action, if you've got longer spans, or a lot of concrete topping is needed for acoustics, we'll use the concrete topping because once you've got a thick enough topping, it's just going to be the stiffest thing and you can reinforce it and it's really straightforward. On this project, though, we only had 1.5 inches of topping, so that was out. And I really hate using plywood diaphragm on top of CLT panels. It just feels like the most ridiculous thing ever because you've got these super stiff CLT panels and you've got this little sheet of plywood and you're expecting to do the work and there's no way that it's going to do the work. So yeah, we typically will use the CLT panels as diaphragms. It's easier to do in Canada than the US, but then that's getting easier and easier in the US and the new NDS is explicitly allowing a CLT diaphragm. So that's great news. But anyway, CLT panels with plywood splines are pretty standard on any mass timber project with a mass timber diaphragm as like a really cost-effective way to tie panels together. And then often the cost and the complexity ends up being in how you drag load around, which is usually some form of strapping on top of the panels. And that load path tends to require a little bit more careful thought.
So you landed on buckling restrained brace frames for the structure. It seems from my research, this may be one of the first mass timber structures that utilize BRBFs with utilizing wood columns and wood beams and a wood diaphragm. There's been a few structures out there where they did use BRBFs, but with steel beams and steel columns. What was that process like?
That's also been my research as well, but
a BRB, or buckling restrained brace, is a structural brace in a building, designed to allow buildings to withstand cyclic lateral loads, typical earthquake-induced loading. It consists of a slender steel core, a cementitious casing designed to continuously support the core and prevent buckling under axial compression. Because BRBs achieve a high level of ductility, stability, and repeatable hysteresis loops, BRBs can absorb significant amounts of energy during cyclic loads such as an earthquake event, resulting in a response modification factor of 8 as noted in US codes.
Going into it, it felt very natural to be looking at BRBs within a wood frame because we were looking in the context of other products within a wood frame. So we were looking at Tectonus within a wood frame and QuakeTech within a wood frame. Concept there is whatever device we use, whether it's BRBs or Tectonus or QuakeTech, that's where the ductility is focused and the energy dissipation is focused. And the rest of the frame needs to be able to withstand the drift and needs to be able to withstand the loads, but doesn't actually need to participate in the system in any other way. So when we landed on BRBs and looked at doing it in a wood frame, we looked at what some of the considerations are if it were a steel frame, in terms of overstrength that you have to consider and drift compatibility and all of that. And we were really careful to make sure that we weren't introducing any rotation within the connections or that the connections could handle that rotation. So we weren't trying to put anything unexpected in the wood. But then once we did that, it's just a matter of making sure that the weakest part is the BRB and everything else can handle all of the additional forces going on at some overstrength. So it was not a complex process, except that the forces were high. So like we ended up having this was a 4-story on one concrete podium. The lower 3 stories in the brace frames have continuous columns, so we didn't have to deal with any column to column splice, which would have been really complex when you have brace connections in there as well. And because the owner was also the developer and the builder, we could talk to them early on about what does it mean to put up these 3-story timber columns as you're erecting the rest of the structure, and is that manageable? So yeah, things like that we had to really work through, and the detailing was a good amount of work. That this was a really in-depth process, but it never felt like this doesn't make sense, this isn't going to work, these systems are incompatible. It always felt like, yeah, this, if we do this carefully, we'll figure this out and we'll do this properly. And we had everyone in our office kind of weigh in on it. We had a lot of people involved in how to make the system efficient, given that it is a hybrid that there isn't really a precedent for. After we started sharing some photos and publicizing this project, we did get in touch with some researchers out of New Zealand who are studying this exact system, it turns out. And it was interesting speaking to them because they were coming to many of the same conclusions that we had come to, and their research was really promising. So it'll be nice to see the outcome of that.
Wow, that's pretty neat. That's cool that publicized it and there's somebody already doing it, and it must have felt pretty good to come to the same conclusions as well.
Yeah, it was. We were speaking with them, and it was kind of a relief when, they're saying that they found that the most efficient connection is what we found that the most efficient connection is, and the performance of these connections were actually quite good. And it was like, okay, good. This is useful.
So this might be a little difficult with only being able to describe it over audio, but could you kind of walk us through what these connections looked like? We were able to get some photos of these connections. Take a look at the link below in the show notes.
So the basic timber steel connections are just tight fit pins. So we, as I said before, the ductility and all the yielding of the system is focused in on the BRB, and we know, the steel strength and exactly when the yield happens, and we can tune that really finely. So everything else was over strength, but even so, just for good detailing practice, we always make sure that we use really skinny tight fit pins or bolts that if they're to fail in the appropriate yield mode. So we want to see the pin or the bolt yielding. We don't want to see any wood crushing. And then when that happens, that offers kind of an extra degree of resilience, ductility if we need it. If anything goes wrong, you have a little bit of extra capacity in the steel yield mode governing. So basically the result of that is all of the wood to steel connections have rows upon rows of these skinny 16 mil diameter or 20 mil diameter. So that's 5/8 of an inch and 3/4 of an inch tight fit pins, which ended up really being quite gorgeous. Like these connections are really nice to look at. I don't know that Structure Lab would agree. They grumbled a couple of times about installing these connections, that they're some of the more complex connections they've come across, because when you have 35 tiny tight fit pins in one connection, that just becomes really tough for tolerances. But they did it. To their credit, they did it. So yeah, we've got a lot of those connections throughout, and then we avoided column to column connections wherever we could with column continuity. And then we sort of cheated in the hybrid lateral, like wood steel lateral system, because the horizontal beams in a typical brace frame would be part of the frame used to drag load, especially since we've got chevron frames. But getting the load in and out of those horizontal beams was starting to be really, really onerous and expensive. So, and we had the luxury of a raised floor on this project, which I've never had on any project because they always get value engineered out. So we put a steel tie-in above the beam and kind of hid the all of that within the raised floor. So how it expresses is you have these braces kind of disappear into a glulam beam really cleanly with no connectors or minimal connectors. And then you have a steel to steel bolted connection with this tie that's right above that beam and above the diaphragm. And it's just such a delicious cheat on a project like this.
Did the BRBs come from Core Brace?
Yeah, Core Brace provided them. They were fabulous. They were pretty clear that this was a new and unusual application for them. And we very early on decided with them that their scope would end at the connection to the steel knife plates, and that we would be designing the rest of the connections because we had the timber experience within our office. So, but they were really eager and excited to see and to have their braces in a wood frame.
Yeah, I was really curious about that. I've worked with them quite a bit, and they'll typically design the gusset and the gusset connection to the steel beam and column, and I was interested to see how they dealt with that interface. And I think that scope makes a lot of sense with their experience and their specialties really being in the steel world.
Yeah, that was an easy thing to define. I think everyone was happy with that outcome.
Anything else that you can think of that you want to bring up about the structure or something unique?
So one of the challenges that took us by surprise a bit on this structure was if this were a typical concrete or steel building, well, if this were a typical concrete building, the lateral system would just continue all the way up. Because we switched from braces above the transfer level to concrete walls and concrete cores below the transfer level, and getting the column alignment above and below the transfer level was really challenging. We ended up having a lot of struggle at the base of the brace frames, where we had to transfer those forces out through the transfer slab into the shear walls and the cores. So we're doing a lot of tall wood projects that are super interesting projects, and what we're trying to enforce on all those projects is that the columns can transfer out at the transfer level, but any brace frame columns really need to be coming down or have a wall or something below them, so you don't have any softness. Because in the modeling of this project, we were finding that where there was nothing, just suspended slab under the bottom level of brace frames, the load distribution was hugely impacted. So our assumptions of what brace is taking how much load, it made a big difference on what that slab was doing. And it's more, I think, noticeable for the taller wood buildings, the up to 12-story buildings. But certainly for a building like this, it did make a difference. So I always encourage the engineers to try, just for the brace frames, to avoid the vertical transfers.
Yeah, I'm looking at the connection actually right now. I think to your guys' transfer slab, and are the columns? I guess are the anchor bolts cast in place? Did you guys utilize an embed plate?
We had we went through a couple of different iterations of this, because we ended up having relatively little tolerance available on the base plates to get those columns right. And this is something that we and the whole project team were hyper aware of from the very get-go, that there just wasn't a ton of room to play with here for concrete misplacement. The anchor bolts were just cast in and surveyed several times, and the contractor was really confident that they were going to be fine. We were really anxious that they weren't going to be fine. Some of the bolts were out by maybe 1/2 inch to 3/4 of an inch, but most of them were bang on. Way better tolerances than I normally see on base plates for projects like this. And I wouldn't go that close to the line again. I wouldn't leave that little tolerance in the system again. But in the end, I think we just brought it up every chance we got. They surveyed the hell out of it, and it worked fine. But yeah, I was really worried about that.
I guess what was the driver of using a transfer slab and not taking the mass timber all the way down to grade?
Above the transfer slab was office, and with a very regular layout, and below the transfer slab was very different restaurant and some other occupancies, but totally different occupancies than above. So bringing the braces down, it wasn't going to work with a layout. And then we would be asking the braces to handle such a massive amount of weight from the transfer slab as well. Mm-hmm. Plus, all of the core wanted to be concrete because of the fire requirements below that level. So we never went deep down that path of looking at bringing the braces down. It just was clear from the start that transfer down wanted to be concrete.
I guess your ear to the ground with mass timber and the whole industry. Is there anything you like research-wise or technology that you see coming out in the next few years?
We're going to be seeing a lot of tall wood buildings over the next couple of years, 2 to 5 years probably. There's a lot in development now within our office, and that means in other places as well. There's a lot of people working on these tall wood buildings. So I think that's going to be the next really high profile thing when you start to see these being built and being lived in and being occupied. So I think that'll be the next one. Some of these technologies, I'd really like to see Tectonis go further and raising it on one project in the US. So I'd like to see more variances in the lateral systems available for timber lateral systems, because it's great news that the codes are starting to bring in CLT shear walls, but the way they're bringing in CLT shear walls offer very little opportunities for ductility. So for high seismic zones, we really need something more advanced. So I'm hoping we see some movement and research on that, and there has been over the last couple of years. So that's great news. And then always just progression on connection technology, codes, experience, and every high-profile mass timber building that goes up adds to kind of the comfort of everyone else on these mass timber buildings.
So for any of our listeners, how would you describe a tall mass timber building? How many stories would that be?
Not getting into kind of the code language of tall, but in our office, we'll consider tall anything above 6. And in Canada, the 6 to 12 range, which in the US is the type 4B, I believe. That's what we're seeing a lot of in development right now, and what we're going to be. And I'm seeing a lot of that happen in the US. I'm really interested to see what happens in the type 4A range, which is 12 to 18 stories. And then we're also seeing a lot of interest in kind of timber systems being developed by a couple of big players, like timber modular system, either volumetric modular or essentially flat pack. Some firms are going to go far in the next little while at developing these systems and having buildings using these systems be really, really cost effective and efficient to build.
I think it was at the Adidas building in Portland, Oregon. They were using like a double T kind of shape where the CLT panel on top, and then they attached 2 beams to it, and kind of seemed like trying to stick to, a traditional 30-foot by 30-foot steel frame by just supplementing it with kind of a double T system.
Yeah, there's a lot of that going on where everyone wants to do 30-foot spans to compare with steel buildings and some concrete buildings, and 20-foot spans are dead simple in timber and really, really efficient, but not every building is appropriate for 20 by 20 grid. So finding good, efficient, repeatable systems for that 30-foot span that's a real sweet spot there. The double T is great. It's kind of, in the timber world, you look at anything that precast concrete can do, and there's a really good chance that timber can do it, and maybe even better. So definitely the precast concrete world has been a big inspiration for the timber world, and kind of we take that and then build off of it. And you see that in the rocking walls that have been the research and the work that's been done on the rocking shear walls, which is a technology that came out of concrete. The prefabricated floor systems and building systems like the double Ts, or there's the potential for essentially hollow core, where you take the double T and you put a bottom on it, or there's different timber concrete composite opportunities that can be prefabricated, or at least partially prefabricated. And then there's building boxes and turning those boxes into buildings and how you do that. And like all of this is study and research and development, and it's really a lot of fun.
Yeah, every time I look into mass timber, do a structure in mass timber, it seems there's just so much excitement around it from everybody. The owners want to be involved, the architects want to be, very involved with the structure. I just think it's such a cool process, and there's just, I don't know, the excitement behind it is, just makes the project that much better.
Yeah, you're absolutely right. I think working in timber, people get really excited about this material and what you can do and what the end product can look like. I know I do.
One of the last questions we like to ask everyone we interview is, what do you think makes a great structural engineer?
I think it's someone who likes to solve hard problems. Like, we're just creative problem solvers. That's the heart of structural engineering. It's based in physics and math and material mechanics and all of that stuff. But structural engineering is all about being handed a problem and finding a really logical, elegant solution that fits.
Well, thank you so much for joining us this week and teaching us, along with our listeners, about mass timber and the use of a kind of a BRBF system along with mass timber. And we really appreciate having you on.
Thanks so much. This has been a lot of fun.
All right, that's the end. Thanks again for listening this week. I hope you learned as much as we did speaking with Elena and all of her experience in mass timber. Let us know if you have any questions by reaching out to us on LinkedIn, Facebook, Instagram, or email. You can find those links and more information about the Timber Connections for this week's episode in the show notes below. Have a great week.